This is from this book, okay?
Case study
Pattern
3.
recognition and neural networks. I think the same data sets also appear in some like regression book about linear model. This is such a famous data set as well. So I want you to look at it and use a tree model instead. Anyway, have the instruction how you can read this data set, including the trend data set and the test data set. Trend set comes with 2 formats with missing value included. So see how we deal with missing value. But here I ask you to do a tree model for the result. So you have, well, this is only for tree models, so I'm not asking you to do more than that. So you have about 1.5 weeks to do this. Okay, is that good enough? No.
Oh.
I assigned this yesterday, so not fun.
We're just doing tree models? Sorry, I haven't read it.
Just do tree model. Yes.
Okay. And use a 10-fold cross validation. Try your best if either use a 10-fold cross validation or 5-fold cross validation. Of course, the default is 10-fold cross validation. So try this out. So here, this is a data set.
Default is 10-fold, right?
10-fold.
Okay.
The default is 10. Anyway, it's right there. And I believe the same data set, except probably in different organizations, also from this package. Let's see if I can find it. We can say that. Let me see if it's in here. Right here, it's PIMA, Indians, diabetes. So actually, this is part of this ML bench data. Okay. Probably different software they organize different way, but for this case study, I ask you to go in there and using this setup given in this website. Okay. They have trend data set in 2 formats. Okay. This 200 rows of trend set contains only non-missing value. Okay, so complete cases. Okay. Actually, the original data set has hundreds incomplete cases. Some variables are missing. So. And here, this is a test data set. So anyway, so I give the instruction how to read this data sets already. So try to use that. Just use these 3 commands to do that. And of course, after this, you want to say save.image, parentheses, right? Just save the result. Or you want to do this, you might want to save into, after this, this is all cases supposedly. So let me just write. So you want to save this result, this PIMA.trend trend2, and then here we have this PIMA.test, right? You save this into our image file, for example. This is of course, if you want to put it in appropriate folder, that's fine. So maybe you want to put it to another folder that is so parallel to this, with this your current folder. You can do this. You can put this dot there and then here. It's just up to you. Whatever the organization you wish. Okay, so you can
You can use it to replace that if you want. Okay. So then here, this is your current folder. Okay. And then here, of course, this data folder is in parallel with that. Okay. So your current folder, you're working under this environment. Okay. So by doing so, you save this under this, your current, this the other folder that is parallel to your current folders and whatever that is. So by now you know how to organize this, right? Your project, isn't it? Okay. Should I repeat this? So anyway, so you have this data set. Well, I think it's good to organize your data first before you try to do things. Okay, so here this is for case study number 3. And last time I think I owe you this class note number 15, but actually this is from Caret package. It's already in there, except that I have the older version that they have some changes from older version to new version, so those commands will no longer exist. That's why last time when I ran this, it fails. Here, this new version. But anyway, you can see this from that variable importance vignette from this Caret package. So it's running that. Okay. So let's run this example. Probably in a smaller size. This is from this multi-drug resistant reversal agent data. How this we already talked about last time, so let me just run this. So this is to acquire for the data set, and then here we know that this is a 528 observations, 342 variables data set that we have from last time, right? And we have to talk about that. First, try to remove some near zero variance variable. So here, this is what we already talked about. Anyway, and it's already reduced down to 297. Okay, so 47 variables are considered to be almost constant, right? Okay, so that's why almost constant has no predicting power. So we exclude those near zero variables. Okay? Near zero variance. So here, these are almost constant variables that we exclude from our data set. This is a place they actually reorganize it. So here, this is new ways. In this package, they just pre-process the data and then predict. So basically, this is center and scale. Actually, you don't need to use this. R has this built-in command called scale. Okay. This is command actually to scale that. Okay. Scale is a command to allow you to center and scale your data set. There's another. But anyway, let's just take the one that we have from this package and pre-process the data. And the data now will be columns are center and scale separately. Okay, meaning that by default, when you process the data, remove you center the data around the mean. So subtract mean divided by standard by center. Okay. So here these are the center. And set up the training control. We want this to keep quiet, so it's not train. During the training, okay, this verbal iterations before, so set it in quiet mode with the result. Here, this is part actually we didn't talk about, but let's just for the comparison. Here, this is random forest fit. Okay. It takes a long time to maybe 1 or 2 minutes to fit this, so let's just do it. So here it's still fitting. Anyway, we can still just go to the next commands and let it fit, and then each one takes a while to do that. So anyway, I have this all run to anyway, they're still running the random forest fit, still running. Okay? And followed by this partial least square. At the moment, we didn't cover random forest, we didn't cover partial least square fit. Okay. Well, suppose if you learn from linear model 6, was it linear model 662? If you learn about partial least square, maybe I'll explain that in time. That, okay. So here we have this all the result completed. And then you can find and remove columns most correlated with others using, say, cutoff. Okay. So I have this result. So first, just take all the variables in, and then here, this is the next set will be the sort of reduced set of variables. Okay. In addition to removing the removing the reduced or removing the near constant variables. Okay. Here we also exclude columns most correlated with others. Okay. By using this cutoff, that's a default cutoff, 0.90. And it's done by this fine correlation, and there's additional arguments actually saying that cutoff is like 0.90 as a default. Okay. So suppose we do that, use the default cutoff. Okay. And now we can see that we reduce that from 297 columns down to 94 columns only. Okay. Within these 297 columns, a lot of them usually correlated with very high correlation. Okay. So it's good. Okay. So reduce that. Okay. So reduce columns the most correlated, and then we refit this random forest and partial least squares. So let's finish this. I want to explain this later on. So it is still fitting. So it's fitting partial least squares now, and then following that will be model-free variable importance. Okay. Okay, so here let's look at a scalar plot matrix of variable importance of the three methods. Okay. Suppose we do that. Okay. So we collect this into data frames that we have. Okay. This is to include all 297 variables. Okay. These are the pairwise. You sort of plot in pairs of with the same variable, of course, right? And how they are correlated. Okay. These are variable importance measures over random forest, over PLS, and over ROC. So, for example, this would be a point where this is variable importance measure for random forest, and for that same variable importance for PLS right here. So, point pairwise. Okay. Now, without excluding highly correlated variables, this is really hard to see the trends. More like, okay. Well, if these different variable importance are sort of near consistent, you should not expect something like this, isn't it? So if one method, the variable importance of one method is about the same as the variable importance for the other method, you should expect like a closer to straight line relationship, isn't it? Here, this is not the case. Right? Here, the plot is done by this, and this is. Well, anyway, this SPLM, this is from lattice package. When you load this, the lattice package is already loaded, and you can see this variable importance. Okay. Scalar plot matrix is produced like this. Okay. With all 297 variables, okay. It's hard to say that they are consistent, right? Isn't it? Okay. So happen random. And most this, the variable importance in random forest, okay, is kind of because the variables enter into the models randomly because the way the algorithm is. So you see more randomness in random variables because of these highly correlated variables. Okay, So you have set of highly correlated variables, and these variables will enter into the model randomly. That's why we have this result. And look at this scalar plot matrix after removing highly correlated variables. And remember, we have how many variables left? We have this 94 variables left. And look at this 94 variables. We plot the variable importance. The pairwise variable importance. Now you can see. Okay. You can see more consistent result. So indicating basically, well, we only need to look at this 94 variables. Of course, these are based on this, the algorithm that implemented by this package. Okay. But you're going to get a nice model, which is this. Okay. So you see a more consistent result now, right? Ideally, you want the variable importance in one method is just sort of consistent with the variable importance in the other method. So ideally, you want a straight line. But here, of course, this is not exactly a straight line, but closer to being a straight line. Okay, so basically, we can look at this reduced set of variables with this 94 variables. Okay. We want to do this correlation, this correlogram. So with this 94 variables altogether, it's really hard to visualize. Okay. Let's say we look at top 30 variables. Okay. So here I set n top equal 30. Of course, you can change that to maybe top 20 or something like that. Okay. It's nice when you program this, you just when you program this, do this. All you have to do is just change this things here. Okay. If you decide to go with top 20, just change that. And you don't need to change the code following that. Okay. Suppose here I create a vector, say VARS. This is to collect, okay, 3 lists of variable names according to this order of this variable importance. Okay. Suppose I want to collect that. Okay. So here 3 lists means corresponding to the 3 different methods, right? We have this random forest method, we have this partial least square method, and then we have this model free method. Suppose I want to collect this, okay, for the top 30, okay. Here, this part is very similar to what we had done before. Okay? So here, let me just run this result. Okay? That's me, right? Over that. Okay? So here, these are variable importance plot according to this 3 method. Here, I only listed top 30. Okay, these are for each method. Okay, the variable importance measures. Okay. Now here, of course, here in this data set. What we have, the response was what? That was our response. This MDR class, there are only two levels, right? I think this is continuous variable. Is it? MDR class. What was this in there? I forgot about that. What's that? Oh, here active and inactive. There's 2 classes, case. And we do variable importance. We only look at the variable importance of the active class. Actually, I forgot about that. Here, I'm looking at the first column. So you look at the variable importance of active group. So okay. So I look at it already. So we run this variable importance and plot the result. Did I plot this already? Okay. So here, these are the variable importance of this. Okay. Listing the top 30s for each of this group. Okay. Suppose now I want to produce this choreogram by combining these 3 data sets. Okay. These 3 lists. Okay. So we want to create this choreograph. Okay. Let's look at it. Okay. Yeah, we already have this MDR described in MDR class, so we don't need to redo that. I don't know the reason why I put this here. Okay. Anyway, we don't need to run this one. But just run this. There's a command called union. Okay. Kind of interesting that you can do this. Okay. It's a union, this variable list that we already created up there. Okay. There's no. We already created this list of variables. Okay. Yeah, these are the 90 variables that we have. Okay, over there. Okay. And of course, well, remember I kind of gathered this together with like three separate lists. The first 30 is variable importance for random forest, right? From 31 to 60, these are variable, or the variables in the variable, the top 30 variables for the partial least square, and the last 30 will be for that. Okay. Of course, there are some repetitions in this result. But you can use this. You can use union to eliminate this subsets anyway, or you can use unique. There are different ways of doing that. You kind of use the union commands to do that, so you can see. Let me just run this and see. You can see. Okay. Excluding excluding the repetition. Here we have this down to 40, about total of 40 variables. Okay? So basically, we are trying to display this choreograph of these 40 variables by doing that. You might as well just use unique VARs. That would do the same trick. Okay? Same result. Okay? Instead of that, do unique. Okay? This will result in the same result. Okay? Well, I take this opportunity to explain about union and intersections as a set variable. I have these foreign commands that are actually using intersection. Okay. So for now, let's look at the unions of variable importance. So this is what you see in this. Okay. In this, the top 30 variables for the random forest, and these are the top 30 variables for PRS. Okay. And actually, if you combine these three, they are total 40 non-repeated variables. Okay. Does it make sense? Okay. So, or of course, some set has some variables uniquely, not in the other one. Okay. We do that. So let's run this correlation matrix of this the unique variables that in this. Of course, this is for top 30, right? From each one. Okay. So union of these three is result in the 40 variables, okay, not just 30. Okay. And now this the rest of this is like the same command we seen before. Okay, so you can roughly see that it's kind of with the two groups. Okay, one group that they are with positive correlations, and the other group with negative correlation. Not exactly. Okay. Like here, this one group variables, okay, and looks like there's another group of variables here, right? Okay. Anyway, it's really hard to see for this, so many variables. Okay. Because you can decide to make the size smaller. Actually, I did CEX equals 0.75. That's probably not small enough. Okay. So anyway, you can make this carrier expansion to be smaller, so that it's probably easier to see. You can change this. Let me make it smaller. Make it 0.6. Hopefully this will be better. probably see clear what variables are involved in this, right? So there are a total of 40 variables. Okay, these will exalt the top 30 variables in these three methods combined. Okay. Well, here I show you alternatively, instead of looking at the unions of variables, I look at the intersection of the variable. Means that only look at the common variables in this variable importance, the top 30. So here, this one, you run this index here. I think a better way is just let me uncomment this one, so we run both comment here. Here, produce an index of intersecting the variable importance. Okay. So use intersect. Okay. This will become the intersection of these three sets. Remember these variables 61 to 90. These are the top 30 variables for model-free method. Okay. And here, this is the top 30 variables for random forest, and here top 30 variables for partial least square. We do this intersection first, and then intersect with them. Okay. I guess that there's a limitation of this intersect command. You only can do intersect of two sets, not three. So that's why I do this twice. Okay. So you use this intersection, and then you produce a correlation. Kind of interesting. If you're interested in look at what this variable asks. Okay. So they are 20. Yeah, there are 20 variables in common, right? So of that, remember I display this partial list. I mean the variable importance of these three methods. Okay. There are 20 variables that appears in all three methods. Okay. So suppose we run this subset and then do this again. Okay. Let me uncomment this one so we have labeled that result also. So here these are the variable importance, and probably now we can see clearly there's two different sets, right? Two different sets of variables. The set one was they are positively correlated with some, most of them with some moderate to larger correlations. Okay. And remember at the very beginning I only used a cutoff of 0.9, so that's why you can still see some large correlations right here. There's a 0.73 right here. This is 5.89. It's hard to see from this. Okay. Or maybe you can decide to have the cutoff not just at 0.9. You can have cutoffs like 0.8, even smaller correlation, to decide to exclude those variables. Okay. Anyway, I'll let you try the other thing here. If you want to look at only model free, this is the command to produce the correlation and then follow with that. I put this all in the comment so you can look at individual. Okay. Like this one, if you have this correlation matrix for the model free result, okay, you can run with this command and then just do this again. Starting from this. Probably need some better control of this result. This is quite messy because we try to ask them to print everything, right? So maybe if you run this, I should just turn this label off, right? Okay. So, anyway, that's good enough. Okay. So here, these were the result from that class note 15.r. I already modified this so you can download this again. So we should change it. So now today we go into a new method that we didn't see before. This is more like a hyper result. Okay. At first, looks like this is really good result because, well, as you can see, the model fit I will present later in iris data. The error rate is like 1 out of 150. Or if you look at the trend set, it's only 1 or 2 out of like the trend set of size 45 or something like that. So looks like really nice. Okay? But it's not really the case. Okay? It's called neural network. Okay? Well, of course, this is kind of a and anyway, this is inspired by our brain works as a neural network. Okay? Inspired in this biology field. Okay. Well, hopefully you can see this. Okay. This is like a picture of a neuron. Okay. And now here these are networks of neurons. Okay. Okay. I'm not supposed to be the one to explain this. You are coming from biology field, so you probably explain better stuff this result. Okay. But pictorially, you can see later on we have seen the graphics like sort of showing that. Okay. For the human learning in the neural networks in the human brain, this is about we have approximately 10 to the power 10 neurons. This is a huge number, right? Okay. Very complicated system. Okay. And between 10 to the power 4 and 10 to the power 5 connections per neuron. Okay. So even the complexity even higher now. It's the added complexity. Okay. And neuron switching time is approximately 10 to the power minus 3 seconds. Okay. So the switch on off probably 1,000 operations per second. Right? You can try to think about this. Okay. And scene recognition time is approximately 0.1 second. Okay. I'm not sure this so-called scene recognition. This is more of like recognizing the picture. Is it? Anyone can explain better? I'm not really good at this. So we can recognize pictures, 10 pictures per second. Does that mean this? I'm not really sure about that. Anyway, but of course our interest is not in this, right? We just follow this kind of system as an algorithm to do a classification task. Okay. Okay. Now here this artificial neural network. Okay, was proposed by these two authors. Okay, in 1943. Okay. And they first do this model with this artificial neural network. Okay, so well, in a sense, it starts with actually there are other models like sort of in this format. Okay, like projection pursuit method, projection pursuit regression, and there's a structure equation modeling. It's also this kind of thing here. But the thing is that here, these are the input variable. Okay. Well, of course, you can also increase the constant term here. Yeah. Now input variable 1 here, that's a constant term. Okay. Through these input variables or our feature vectors, right? This is what is called in machine learning. Feature vector as an input. Okay. They're going through some hidden layers. So hidden layer, this is kind of black box, right? So you won't be able to see what's going on within that. Okay? With this hidden layer or hidden layers, you could have multiple hidden layers. Okay? So through this input into this, and all the mysteries just happen to you. Okay? So you don't see what happened, what's going on. And then there goes output. Okay, okay, so here this is like the artificial neural network. Okay? Actually, this ANN models from that. Okay, this is like a picture, schematic part of the neurons. That these are sort of dendrites, sort of receptor that they would accept information, right? So the information channel through this is like our input, and the gray box is right here. This is the cells just process this, right? Maybe with a hidden layer or number of hidden layers, okay, in there. And then this exon just channel the process information, okay, channel through that, and then to this, to output. Okay? And the synapse just kind of transmit the process information to another cell, another neuron. Okay? Or you can consider this as output, right? This is output result. So input and hidden layers and outputs. Okay? If you're interested, go to this webpage and see this result. Okay, interpreting this. Okay. And this artificial neural network basically try to simulate this, how should I say, emulate this neural networks in our brain. Okay. So here these are input variable, and we could add one. Here would be the constant. And in this neural network terminology, that constant is named is called a bias. Okay, the constant term is called bias. Okay? So bias kind of impute into that. Okay. So with this input variable, and the input variables are weighted. Okay, and going into the hidden layer. Okay, and hidden layer, this is basically through some kind of transfer functions or activation function. Different name for that. Okay, the transfer function or activation function, and usually this functional form is logistic. We're going to explain that. Okay, and majority of this is logistic function. Okay, this is that. Okay? So xi is input received from neurons or environment, and total input I is then formed from the weighted input with weight. Of course, weight W0 will correspond to that bias term, okay, with input from 1 on there. Probably I should draw that too. So anyway, so here we have this result, and W0 will be constant as long as the bias. So that's the terminology used in artificial network. Okay. And the transfer function, remember this is like the processor, the process your information, right? This information combined from all the inputs and process that, okay? And then through another layer, another transfer, another function, okay, that will transfer to the output. Through this transfer function, okay, with the input, the combined input, okay, you apply the transfer function to the combined input, and there goes the output. So go to that. This kind of mysteries in this happen in that. Okay. Now here, these are the typical. So some of this example. This is probably those ones used most. Okay. Logistic one, those logistic probably happen to a lot of situations. Okay. Majority using logistic transfer. Okay. So here this is logistic transfer function. Okay. You know the function values is in between 0 and 1, right? Okay. So it's this kind of transfer function. And here this is how do you call this? Hyperbolic tangent, right? Is it called hyperbolic tangent function? Tan H. I couldn't remember the terms used in mathematics. Okay. I think this is called hyperbolic tangent function. It's in this form, and here this is like a switch on and off, right? Switch on, and you have jump to this is like the impulse function. Okay. That I think there's a typo here. It's supposed to be if x is less than 0, then you have 0, and if x is greater than or equal to 0, greater than or equal to 1. There's a typo here. Okay. Then you have 3 or 1. Okay. This is supposed to be greater than or equal to 0. Okay, so these are some transfer function examples. Okay, and in a sense, this logistic transfer function, this is like logistic regression fitting, except there's some add-on layers into that logistic regression. Okay, so in a sense, related to that. Okay? And the transfer function usually takes one of the forms, either linear, transform, logistic, and threshold. There are others. I use other transfer functions like there's entropy, information theory, and there are others. I forgot how many of them. You look at health documentation about neural network, there are different types of things. They are mutually exhaustive and mutually exclusive. You can only set up one. Okay, you cannot use both, two or more transfer functions. Only one type of transfer function is used. Okay. This hyperbolic tangent function basically is a mix of linear It's a linear transformation of logistic transfer function. Okay? You do this transformation actually. Okay? Anyway, because of his mysteries, here this is like a schematic view of this artificial neural network, and the particular name for that feed forward 432 ANN is that in the input layer you have 4 variables, input variable, right? Okay. You can include one more constant. Constant is not counted in this four inputs. Okay, so constant layer should be something like that. You can always add a note here indicating 1, which is a constant that we can fit into the inputs. Okay, so what that means here, you have note which is 1. Okay, and I can fit into any one of these nodes in the hidden layer. Okay. Now, if you look at this schematic class, that we don't have, say, the communication between the nodes within the same layer, right here. Can you see that? Okay. So the nodes not communicating with each other. So there's only input, and then here, the input from X1, and then X1 could have output to each one of these 3 nodes in the hidden layer. So, okay. And same for hidden layers. Okay. They are not communicating. So there's no connection between nodes within layers. Okay. And then here we have this output layer. So output of each layer directly goes to outside. This is, and it's called 432 because we have 4 nodes in the input, okay, not including the constant, and 3 nodes in the hidden layer, so 3 here and 2 in the output. Okay. And the number of hidden layers can be 0, that is without hidden layers. Okay. There's a particular variance of this AN is that it allows skip layer. Okay. Skip, here I should mention that. Okay. Skip layer means that you have in particular node that can skip the hidden layer and go directly to output. Okay. That's called skip layers. Okay. So in RAN neural network modeling, the skip layer is allowed. Okay. So you have that. Okay. So in case of having a skip, this skip layers, then you could have 0 hidden layers in that. Okay, so go directly to output. Okay? And the number of neurons in the input and output layers are determined by the nature of the problem. Okay? It depends. Okay? And the number of neurons in the hidden layers is user defined. Number of neurons in input base is just indicating, when I say nodes, here, under neural network, nodes and neurons are interchangeable. Okay? Input base, the number of neurons in the input base, these are the number of feature variables, right? The input variables we talk about. Okay? And output layers, classification, with the classification of 2 classes, then you have 1 output. Okay? This is a difference between them. Okay? Between the first one and the other one, and then depends. Okay. We're going to see that later. Okay. And within each layer, neurons are not connected. Well, this is one that we're talking about. Okay, they are not connected with each other. And neurons are in one layer are connected only to the neurons in the next layer. This is what we got a name called feed forward. Okay, artificial neural network. And each line joining the neurons is associated with a weight. Okay? And these weights are to be estimated, maximized. Okay? There's optimization criteria about that. Okay? To estimate from training data, okay? Based on the information fed in. Okay? And a neural network with a single logistic output is a nonlinear extension of logistic regression. So it's simply just logistic regression. Okay? It's either a continuous output, that is the response is continuous, or you have 2 class output. So that particular just output neuron there's only 1 output neuron. So they have 2 class case. Okay? Basically, it's just give the difference between one class and the other class. Okay? And for K class classification problem, K greater than 2 requires that K output units are required. Okay, so this is what this artificial enable is. Okay. If output units are logistic, then it's linked logistic equation of each class versus the other. These are some kind of just algorithm details, so we don't have to. But after this is break box. This is the kind of break box. Okay. The idea is to minimize, to find ways that minimize this. This is. Remember, this space is just some kind of mean square error, right? Isn't it? Okay. Y minus V transpose Y minus V. This is like a square magnitude. Okay. V is like this is the information. This is after the information, the joint information process, and going through the output. Okay. And Y is what you observe, right? Okay. And you see the discrepancy between what you observe and the predicted result of the insights. The idea is to try to reduce this discrepancy between observed and predicted result. Well, here these are some algorithm details of this about some algorithm baked propagation algorithm is used during the fit to find the minimum. So we don't have to know what it is. Okay. And usually the training data are scaled before feeding into ANN. So then each input has an equal importance. Okay. Scale, there are different ways of scaling, right? Okay. The output or target data are also scaled if the output transfer function has a limited range. Okay. There are two types of scaling method. Okay. One is to fit the data into a range between 0.1 and 0.9. It's done by this. Scaling between 0.1. This is very simple, right? Okay. You get x minus x minimum over x max minus x minus. This is scaled to 0 and 1, right? Okay. And then you kind of at this 0 and 1 scale vary into 0.1 and 0.9 because the length is 0.8, so it's kind of rescale that and shift the location. Okay. So scaling the data into range by this. That's the first scaling method. Second scaling method is through the standardization. Okay. So standardizing variables, so then the input variables have equal importance of the result. Okay. So this artificial neural network.
How do you, excuse me, how do you choose the importance of each of the variables?
So the variables are very different nature, so you cannot use the variable directly. See, some variables with a larger range, if you didn't scale that, the variable with larger range would dominate the result, right? Isn't it? So we need to do that. We do that. So you put them all in the same scale.
Just by looking at each variable individually and its
and
variance.
do it individually. Yes. Okay. So suppose you do this method, then you apply this uniformly to all the variables. Do not mix these two. Okay. Either do this or do this standardization. Okay. The reason they choose this range, I think there's probably some particular reason why this is chosen. I think it's related to the algorithm, so that's why I do that between 0.1 and 0.9. This is rather strange, right? This is feed-forward neural network. This is input cells, okay, and hidden cells, hidden layers. Okay. In this case, there is only one hidden layer, so usually you could have many. Okay. And then here from hidden layers, probably the last hidden layers that will just feed forward to our output nodes here of the cell. And so in this case, it's like 3 class. This is 3 class classification problem, like iris data. Okay. And neural network with back propagation is this allows that feed backward. So information will be fed backward and then feed forward again. So like that. Okay. Actually, we don't have to know about these details. Okay. This ANN tends to overfit and tends to overinterpret, or actually there's no interpretation at all. Remember, this is everything, all this algorithm going on is within this black box, right? So practically speaking, there's no interpretation of what's going on there. Okay? And usually it tends to overfit the result. Okay? And if that difficult to interpret, at least probably overinterpret. And it takes many iterations to converge. Okay? So there is some issue about that, and sometimes it may not converge. Okay? And to lessen this, the number of iterations to converge, usually they kind of impose a weight decay. Okay? And usually range for weight decay is between 0.001 and 0.1. Okay? And empirically, lambda is not critical within a factor of 5, meaning that if you choose, for example, lambda equal 0.001, and then you choose another decay about 0.004, the change is not so much, right? It's a fixed factor of 5, so it's not ideal. Okay. And new ANN requires scaling of inputs, and so that's required. So it won't be pretty. So you need to do scaling first. Okay? Let's look at a running example here. I have this 12.R here. When you fit this, the scaling is done inside this neural network function, so you don't need to do that. Okay. Now. And it requires some kind of random algorithm to arrange, to generate this result. Okay. So usually we start with a random seed. Okay. So suppose you want to reproduce the result. You want this result to be identical, so it requires some random seed to start with. Okay. It requires this NNet. And you can see that this is among the very earliest packages in R distribution. It comes with a standard distribution, although it's not automatically loaded as a default. But you don't have to install this package. Okay. And if you look at it within this package, there are only quite a few objects. So it's very small package. So you can see it's that. Well, the author is Brian Ripley, and according to what he said, okay, this is usually the method neural network is overemphasized. Okay? It's not really a good one. Okay? It's kind of just a hype about this thing here. Okay? Well, of course, we get to know the different algorithms and see what's going on here. Okay? So first, you require this NNet. This comes with a standard distribution. No extra installation required. Okay. So here we load this neural network inside. Okay, so NNet. Okay. And we set some random seed. Okay. So here I don't have time to go through what this random seed is. It uses maybe I should say. It uses some information from a dimension 623. Something like that, different numbers. It's called Mersenne twisters. Anyway, so this is really a really nice random number generator. But anyway, let's not worry about that. Some of these graphics process units even sort of install this hard-coded as a hardware of this Mersenne twister random number generator. So it means this is really good random number generator. You know this GPU, graphics processing unit. The original idea was to generate the graphics like you have in your computer, right? So in the old computer, you have this graphics chip, this GPU in there, and it serves as a slave to CPU. CPU is the most important thing, the central processing unit. But now GPU is competing with CPU for computing power. Okay? So that's why they install this in GPU with like this machine twister, and it was a really nice one. And now super fast computer have to use this GPU. Okay? I think last year, maybe I shouldn't talk about this. Last year it was a K computer by Japanese that run, I think about 6 or 7 petaflops of calculation per second. You know, petaflop is 1,000 times of this teraflop, and teraflop is 1,000 times like what's it, gigabytes, right? So this is 10 to the power of 6 times gigabits of information. It processes this many. I shouldn't say information. There are this many operations per second. Okay. So, and that K computer. Should I talk about this? Probably not. Okay. That was the last year, but now this year IBM has this supercomputer beating that K computer. It's about almost twice as fast as that K computer. Okay. So they are competing with this, and none of this supercomputer cannot do without this GPU. They line up GPU in certain ways. Okay, and do this process. What am I doing? Okay, so here, anyway, so here we have this neural network. Okay, let's just look at this. Okay. What I'm trying to say is that this random number generator algorithm is a very nice one. Okay? That's why they implement this even hard-coded GPU. Okay? Now GPU is like a separate processing unit. It's competing with CPU. Okay? That's why this new computers has this power, okay, computing powers coming from GPU as well. Okay. Okay, so let's look at this result. It says that it converged. Looks like it's a nice result, right? It says according to this, the result converged maybe between 80 and 100 iterations. Okay, it only shows after iteration 80, the value is 4.99. This is some criteria number. Okay, try to minimize the result, right? Remember, it's sum of this y minus v transpose y minus v. This is criterion we try to minimize. Right? Actually, this is criteria number, and minimize the final value of 4.922040. Okay, so you can see the convergence here. Okay, so. Anyway, it says conversion. Okay. There's a but there. I'll talk about but later. Okay. And well, let's just look at. Suppose we accept this result, the final result, and you can do a summary of this result. Okay. It's really hard to read this at first. Okay. This is a 4-2-3 network, single hidden layer, right? So in the input layers, we have 4 neurons. We have no problem with that because in this iris data, we have these 4 variables, right? It's sepal length, sepal width, petal length, petal width. So that's why you have 4 neurons. 4 neurons plus 1, the bias, right? That's a big constant, okay? And then in hidden layers, you have 2 neurons there, okay? And the output layers, remember this is 3-class example. This is 3-class problem, right? So you have 3 neurons in the output. But how do you read this? B stands for bias. Remember, every node feed forward to the next layer with certain weight, right? Okay. So here this means B feed into, well, maybe I should draw the picture like this, okay? So here this is first one, x1, x2, x3. Oops. Names. Okay. So x1 is sepal length, x2 is sepal width, x3 is petal length, x4 is petal width. Because we didn't specify in particular order, right? So it just comes with the nature order of the variable. So x1 to x4 in that order. Okay. And according to this, there's a bias in here. So here this is 1. Okay. 1 that will fit with bias, and then we fit with We have two nodes in the hidden layer, right? So let me use different color so probably better see that. Okay. So maybe I should use a different color for this one, right? Because here this is not currently as well. So here this is 4, 2, 3 neural network because we have this many neurons in that. Okay? And the output layers have 3 classes. Okay? 1, 2, and 3. Okay? So here this is Y1, Y2, Y3. Okay? And of course, Y1, Y2, Y3 of course just correspond to these 3 classes. Of course, we can see what are these Y1, Y2, Y3. Class of species, right? Oh, it's not class. What do you say? Levels. Okay, so here Y1 is Setosa, Y2 is the basic versicolor, and Y3 will be Virginica, according to this order. Okay. So anyway, it's just with this. And according to this, you have this fitting. The bias to the first H stand for hidden layer. So here, this is first node for hidden layer was this way, negative 150.02. It's hard to imagine for that. Actually, in this package, there's no plot method. It would be nicer to use a plot method, but it's this. I'm trying to think about ways to present this graphically. It would be nice to have that. Okay? So here, this hidden layer, the bias fit into this first node. So here, this is a first node in the hidden layer. So let me just write H1 and H2, right? This is H1, H2, okay? So the bias fit to H1 with weight negative 150.02. Okay. So it's this result. And then X1 is labeled as I for input, right? So probably easy to see. B for bias, I for input. So here this is the input node. Okay. So I probably shouldn't write X1, X1. This is I1 here. So basically this is our I1, I2, I3, I4. I stand for input, H for hidden layers, and then here we have O1, O2, and O3 for output layers. Okay. That's what you see in this result. Okay. And likewise, here we can see from I1 fitted to H1 was this way. Okay, so negative 433.51. And you do likewise for the rest. Okay. So anyway, that's what's interpreted in here. These are summaries of the result. And here with this final result, okay, the minimum criteria number was achieved. Except that there's a problem with this. It's not really a minimum, actually. It usually requires that a lot of iteration. And by default, you look at health documentation of neural network. Okay? By default, they set here maximum iteration of 100. Okay? And they are among others. Okay? And actually, with this algorithm, for this case, it doesn't really converge. Or at least it converges, but the result is not really the minimum. Okay, it doesn't really. It's only it's trapped in the local minimum. But this is not really. Let me talk about this issue here. What is this? Oh, okay. Here, this is data set. Say more. Okay, so here it's fitting. Right? Along the way, actually, if you request with this function, it also will produce a so-called Hessian matrix. Hessian matrix in optimization contains very important information. If this Hessian matrix is positive, definitely means that you actually achieve minimization. Positive definitely means that all eigenvalues are positive. Okay? So actually, you need to look at that information. Okay? In this case, unfortunately, it's over here. Usually, you're not burdened with this, but you sort of kind of consider this as the final result. It's not really the case. Okay? So if you refit this model, let me just run the first 2 lines here, and edit 1 line of this. Okay. Produce Hessian matrix, the Hessian matrix information. Or I mean, it's not actually Hessian matrix. Produce the eigenvalues for Hessian matrix. Okay. You say HESS equal to H is capital. This, R is case sensitive, so we need that. Okay. And then we also fit with this one. So we use a linear transfer function. Okay. You actually say stop after iterations. And if you're interested, look at the Hessian matrix information. Look at the it's output the Hessian matrix, but we need to extract eigenvalues information. So here you do eigen of this M. Did I call this M1 or M, right? And this M model, okay. And extracting Hessian matrix. Okay. We're actually asking the R function eigen. Given a matrix will produce eigenvalues, eigenvector problems, but we specify to speed up the computation. What we need is only the eigenvalues. So true is values only equal to. So we only need to get the eigenvalues, not the eigenvector. Now we can see that result. We have eigenvalues with mixed signs, right? Some eigenvalues are positive, some eigenvalues are negative. So actually, we are not achieving minimization in this case. Okay? So you probably need to try others. Okay, maybe specify instead of 2 nodes, 2 neurons in hidden layers, you want to have 3 nodes. Okay, this MNET only produce result with only 1 hidden layers, but the number of neurons in the hidden layers is user specified. Okay? Like our case, I say size equal to, right? So we have only 2 neurons in the hidden layer. Okay? The result is not really, okay? It's not really the minimum result. Okay? But let's just take it anyway and see the result. Okay? Can you see this? It's 2 out of 150. It's overfit usually. The result is overfitting result. Okay? Okay, so you can try others. Here, this one, then out. This is for linear transfer function. Okay, and without specifying anything, basic logistic transfer function is assumed. You look at this help documentation. Actually, you have that. You have this then out. You have this entropy, and you have this solve matrix, and you have sensor. These are among the 5 methods you can choose. 5 different transfer functions. The default is logistic. So actually, if you didn't specify anything, these are all false, right? Okay, you can only use 1. So either they are all false or just pick one that is true. And here I say specify lin out, so linear transfer function equal to. So basically, I use linear transfer. Okay. You look at the help documentation. Actually, they really explain that. Okay. So here, lin out switch for linear output units, default logistic output units. Okay, so that's default. Okay, entropy, softmax, this log linear model. Okay. And you specify this lin out entropy, softmax, and sensor are mutually exclusive. You can only specify 1 transfer function. So that's what is going on here. Okay. Oops. This is 1. So. Okay. Actually, you want to skip second one. Even the second one, not really achieving the best result. Okay? Because the Hessian matrix is not positive definite. Okay? We want a positive definite. We want all eigenvalues to be positive. Okay? The third one is not. Let's look at the fourth one. Okay? Let me skip that and then. Okay.
So after we do these analyses, are we
We
supposed
need
to
to check
check
on
the Hessian matrix?
We need to check on Hessian matrix. That's just, okay. And look at this result. Say we set C and ID trend. Suppose I, instead of fitting this on the entire data set, let me set aside trend set and then the test set. Okay. So here I sample among all the Setosa, 15 of them. Right? Remember, according to this data set, the first 50 observations are from Setosa, right? Followed by versicolor, followed by Virginica. Okay. So I simply just sample the index. Okay. So here basically this is 1 to 50, sample 51, 15 of them. We don't have to do this way. We can do it different ways. So maybe I shouldn't use this one. A better ways or better understood ways would be this. I'm supposed to use this. So here I should do this ID trend. The first one will be the same. And to make it more readable, instead of writing 50, I probably should write 1 to 50. Actually, they are identical. Okay. So we sample the row index, 15 of them from 1 to 50, followed by the second one. We can do sample from 51 to 100, 15 of them. Okay. Virtually, this will achieve the same results. And then you do sample from 101 to 150, 15 of them. This is clear about sampling. Okay. Probably I should do that. Anyway, they are identical. Okay. So suppose I divide this into trend set and test set. Okay. So I take about 45 observations only in the trend set. Okay. So let's run this. So here I use a scale command to actually standardize. Okay? This is standardization. Okay? So trend -5 or minus number 5, count 5 with species. So we just have that trend, and then so here we use data trend and fit with this result, and fit with. Remember, this is decay. There's a decay factor we can set, right? So probably when you try to train this, you better set this. You better set this one, and also in this command also allow you to set initial weights to be from minus RANG to the plus ING. So here this ING now is baseline 0.1. So let me run this with. I can show that this is the case that where you have posted definite Hessian matrix, and run equal to. I run the last one, so I can't add that one. Where is this? Right. So here, suppose I modify this, and then look at this eigen of M4. You can see all the eigenvalues are posted. Okay, so here we do have a minimums actually. So here, this is actually the better result of that. Okay. And if you run this summary, you can see that. Okay. This will be the summaries of this neural network, and then you can apply it to the test set to get test error. Okay. Let me just run this as a complete example. Okay. So you apply that onto the test set, you can see that. Okay. When you predict that, this is observed. The rows are observed species, right? Okay. And then the columns are predicted species. You can see in the test data set, 104 among 105 observations, there are 4 misclassified identities. Okay, so let me stop at this point. I'll continue on this this class notes. I'll skip some of them, but not all of them. The idea is this one here. You also want to check the Hessian matrix. Probably I need to modify my class notes here. I didn't include that Hessian matrix. Okay. And here this is example of extracting the Hessian matrix. Okay.
Class notes 12.
This is 12, note 12. let me modify this with this Hessian matrix then, so we'll see a better result.